Alright, let's continue. Okay, so you are given the piecewise defined function of f. Then the question says, if the limit when x approach 1 of fx exists, find the value of n. Right? So you know that for a limit to exist, it has to fulfill, okay, for a limit to exist. I'll write here, for limit, okay, maybe I write somewhere because, okay, we will revise some concept first. Okay, so for limits to exist, okay, limit when x approach that number c from the left must be the same as the limit when x approach c from the right, and it will be the limits that we want to find. Okay, so this is for limits to exist. Then I saw just now question number 2 asks about continuity. Okay, for a continuous function, at point C, then one more condition, okay, which is your limit, this is the same, okay, exists, means this one, your limit exists. Let me just copy it again, equals to limit x approach c fx, and it has to be equals to f of c, means it cannot be a whole. Okay, it cannot be a whole, it has to be continuous, right? So we'll talk about one-sided limits now. Let me do some revision on one-sided limits. And what I want to talk about is the epsilon-delta definition of one-sided limit. It's actually, I think, it's the hardest part in the chapter limit, right? So let's do a very quick revision. It's actually derived from the precise definition of one-sided limits. If you forget most of them, you can go watch my videos explaining the precise definition of limits. And now I will talk about the precise definition for one-sided limits using epsilon-delta definition, okay, of one-sided limits. One-sided limits. Okay. Alright. So if we have a limit when x approach c, let's say we start from the right first, of fx is equals to L, then you have to choose two numbers for epsilon greater than 0, delta greater than 0. Okay, most of them are very, very, very small positive numbers, right? Then you have to show that the absolute value of fx, I write down the theorem first, then I will explain the smaller than epsilon whenever what? Whenever your c, okay, your c, you have a c, is your x is in between c and c plus delta. What does it mean? It means if you have this one like this, okay, x, y, your c is here. This is from the right, your c plus delta is here. From here to here is delta. It's a very, very small positive number. And your x is somewhere here. Your x is somewhere here. Which means your x approach c from the right, isn't it? Okay, so c plus delta. So you have to make sure that when your x is within this interval, what happened to your y? Okay, in this case it's actually fx. Okay, have to be also be very close to L, isn't it? Okay, your L is here, your L plus epsilon is here, L minus epsilon is here, and your fx should be somewhere here. Okay, your fx should be somewhere here. Which means your fx, the difference between fx and L, you put a modulus, must be smaller than this epsilon, must be within this interval. Okay, so this is for right hand limit. Okay, right hand limits. Then what about left hand limits? It's actually the same. Okay, let me write in blue. The limit x approach c from the left of fx is equals to also L, because I lazy to change the graph vector. This one is exactly the same. Exactly the same. Okay, whenever this is the part. This is the part. Now because you approach from the left, means okay, this is still delta, this is still delta. Your c is now here. Your x is still here. Your delta is here, so it's c minus delta. Means your x approach c from the left. Can you see it? So whenever, how you write your inequality now is actually C minus delta, x between C minus delta and C. Okay, so this is the epsilon delta definition of one-sided limits. I'm not sure if you understand if I explain like this, so maybe let's do one very simple question, writing proof, right? I think this is a part that most Calc 1 student had the most. Okay, anyway, okay, so just do a very simple question. 0 from the right, maybe. This function. Okay, and obviously you know that this has to it has to be only from the right, because the graph of y equals to square root x. You know that it's 0 here, but nothing on the left hand side, right? So you can only prove that if you want to prove that equals to 0, you can only prove that it is from the right. Okay, so the template is very simple. Okay, the template given, okay, always remember, given, choose, suppose, then check. Okay, so given what? Given epsilon greater than 0. It's always like that, always epsilon greater than 0. Because epsilon is what? Very small positive number. Okay, let me write choose here. Okay, choose what? Delta equals to something. What is this delta? A lot of students were stuck here, but actually don't worry, just leave it blank first. And because this delta is depending on your epsilon, okay, let me write down a note for you. Note, we want to find this epsilon, this delta, such that what? Such that, remember from here? Remember from here? So now who is your fx? Your fx is square root x minus what? Who is your L now? Okay, let me write it here. Fx is square root x. Your L is 0. C is also 0. So square root fx minus L, right? Absolute value, right? Is smaller than epsilon. So we need to find this delta. And why do we need to find that delta? Because we want to suppose what? Suppose what? This one, this part. This part. Okay, so see your what's that? You actually took, okay, C in between. Okay, this you have to be very careful, yeah. I will explain later. C plus delta. C is 0 plus delta, so it's the delta here. Okay, so sometimes, but not all the times, you will see that it will not give you x approach 0 here. It will give you a limit 2x approach 1, something like that. So you have to be very careful with this one. So what you always do is you put a modulus first, then you use what? You use this minus this. Okay, so in this case it's x minus 0. Okay, and actually you know that for this you can write it, you can simplify it like this. Why did I throw away the modulus? Because you know that from the graph, your x is always positive. So it doesn't matter whether you put a modulus or not. Okay, and I want to write it like this so that it's easier for me to prove later. Okay, and now what? Now I need to check something. I need to check if my x is within this interval, is my fx, which is my square root x, is it within this interval? Alright, so, and actually it is, okay, I forgot to write one more, it's smaller than 0 lah. It's greater than 0, okay? So, okay, 0 square root x minus 0 smaller than epsilon, right? I need to check whether this is true, and just go ahead and do some algebra. Okay, you know that square root x is always positive, isn't it? So again, the modulus doesn't matter. You just put square root x smaller than epsilon. Okay, so actually we are almost done. I need to make this to look like this. How do I make it? I just say, what? One more step actually. I just go and square both sides. And I think you can see already. Okay, you compare this and this, not this and okay, this and this. This and this. You just let your delta be epsilon square. And you know what? You will just get exactly the same like just now. And you are done. Okay, so this is how you write a one-sided limit proof by epsilon delta definition. Okay, I repeat, the template is given, choose, suppose, check. Given always epsilon greater than 0, choose delta equals to something, and that something is depending on epsilon. And you don't worry, just leave it blank first. Continue with what you want. Then suppose what? The absolute value of this minus that is in between 0 and delta. Okay, this is actually from which? It's actually from this part. Okay, it's actually from this part. Then what? Then check. You see, if you start in, your C is 0 just now. Your this one is just okay. This one x minus 0. Why I say like that? Because sometimes the question is a bit tricky. They don't give you x approach 0. They give you something approach something. Okay, just to be a little bit more careful. Then your x, then c plus delta. Now your c is 0 plus delta, so it's just delta. Okay, then check this inequality. Check this inequality. Then you want to make it the same as this one, so you can choose your value, your delta, based on epsilon. Okay, and that is the end of proof. Okay, let's come back to the question. I think it's this one. Yep. Okay, so we want to find the limit, the value of n such that the limit exists. So again, from just now this one, for it to exist, you know that from the left and from the right other must be the same value, and it has to be unique. It cannot be two values. It cannot be one is positive infinity, one is negative infinity. Cannot. It has to be the same value. So now I want to find the value of n. So very simple. Because this is a piecewise defined function, which piece is approach 0 from the left? It's this one. This one is from the left. And this one is from the right. So just go ahead and equate them. Okay, I'll write down maybe here. I scared I don't have enough space. Okay, x approach 1 from the left of fx equals to the limit when x approach 1 from the right of fx. Okay, then just copy limit x approach 1 from the left of fx is x squared minus 1 over x minus 1. From the left is this function. From the right is this function. Oh, we have the absolute value. Be very careful with that. Plus n. Okay? And now we have a problem, isn't it? If we directly start in your 1, you'll get 0 at the denominator. So you have to use one of the technique from earlier to eliminate the 0 factor, or you do okay, if it is one-sided limits, I don't encourage people to do L'Hopital's because maybe from one side it is defined, but from the other side it's not defined. So a lot of cases, a lot of things happening here. So just go ahead and eliminate 0 factor. And obviously you can see this is actually x plus 1, x minus 1, which is the difference of square divided by x minus 1. Okay, I'm running out of space here. And what about this? Okay, because your x is greater than 1, can we write this as x minus 1 over x minus 1 plus n? Okay, my handwriting is a bit messy here, sorry. Okay, you think about it. Okay, x greater than 1, let's choose 2. 1 minus 2, is it the same as absolute value of 2 minus 1? It is, right? So, you can just do it like that. And why I want to do it like that? Because this is actually 1, and this and that can cancel. Can you submit the 1 now? Yes. If you submit 1, you will not get anything weird, right? So now, okay, you have 1 plus 1 is equals to, this entire thing is 1 plus n. So obviously your n is equals to 1. Finish. Okay. Then if f is continuous at x equals to 1, determine the value of m. Alright? So remember, for a function to be continuous, your limit have to be equals to the value when you plug in the c into the function. Okay, so you are just write the limit when x approach 1, and you already show that from the left from the right are actually the same, so it exists. Okay, f of 1. Alright, so from the right from the left, it doesn't matter, you plug in any one of them, you will just get a 2, right? Just get a 2 is equals to, when x equals to 1, m squared minus 2. So your m squared is equals to 2 plus 2, which is 4. Your m is equals to positive negative 2. Finish.